would like to welcome up our first guest speaker, Mace Barron. As I mentioned before, Mace drove all the way from Gulf Breeze, Florida, to be here, and he's going to be speaking about the comparative toxicity of chemical dispersants.
Okay, well, first of all, thank you all for coming out to listen to us, and appreciate Emily and the Sea Grant folks for inviting me out. So just to give you an overview, I'm going to be giving you a little bit of background information on how oil spill dispersants, their efficacy or how effective they are, and their ecological effects. Give you a little brief summary of EPA's Deepwater Horizon testing program, and then finally, which might be most important to you, so what does this mean? What are the implications for spill response? There's a couple background reports. This is just more or less because you have a PDF of this in case you want to go back and learn a little bit more. There was a real seminal report by the National Research Council on oil spill dispersants, efficacy and effects. This report just came out by the Canadian government. It's really a pretty amazing comprehensive document about oil spill behavior and impacts, and then a few EPA science publications that are the basis of this talk. So what's a dispersant? It's many dispersant products, varied components. As you know, most are proprietary formulations. They don't have to disclose all the specific ingredients. It's a chemical soup. They primarily are surfactants, things that break up. Some will break up oil. They're light petroleum in some of the materials. That's to help solubilize the oil, and different solvents. And again, you guys got a PDF of this, so if I'm going too fast, I apologize. So what do dispersants do? Y'all know they break it into tiny droplets. The key factor here is, can you make the droplets small enough that they become neutrally buoyant? If the dispersion application isn't very effective, it'll look like the oil's dispersed. You know, it'll turn brown, but the oil can recoalesce. So the idea is you have to get enough wave energy and obviously hit it on target. It facilitates biodegradation or natural microbial breakdown of the oil once the small droplets are formed, and allows dilution and dispersion into the ocean. It's really, dispersants are, in general, a rule of thumb is they're only effective on about 30%, less than 30% weathered oil. So if you have a very weathered oil like a moose, that orange moose that y'all probably saw out in the Deepwater Horizon, it doesn't really work very well for that. And there's some chemistry reasons which I can answer later on if you're interested. So the idea is that obviously we're moving the oil slick into the water column. It doesn't mean that the oil goes away. It moves from surface down into the water column. And as you know, it's a trade-off between surface and shoreline impacts versus putting more oil into the aquatic environment where you're exposing fish and other marine organisms. We will see increased toxicity to aquatic organisms that live below the surface. One of the questions I had gotten before coming out here was, so what's the difference between 9527 and Crix at 9500? The most obvious thing you can do is go and look at the MSDS sheets, and you can see, is this a laser? Oh yeah, look at that. You probably, it's maybe too small to see, but this is just the ingredients from the manufacturer. As you know, for 9500, Nalco had to do a full disclosure of all the specific ingredients as part of their approval. But really, they're really similar composition. 9500A, which is the one mostly used in Deepwater Horizon, has more petroleum hydrocarbons in it, real light distillates. In lab tests, they show about the same efficacy and toxicity. So here's some general principles. This is kind of gleaned from about 20 years of dispersant toxicology research. So just some ideas for you here so dispersants don't increase the intrinsic toxicity of oil. all they do is put more oil back into the water. Their dispersants are moderately toxic and are much less toxic than oil. And that was a huge concern during Deepwater Horizon. The public was concerned about the government putting huge amounts of toxic materials in the environment into an already oiled environment. But all the lab tests in general show the same thing, that dispersants are moderately toxic, aren't near as toxic as oil, and don't increase the toxicity of oil. Chemically dispersed oil and naturally dispersed oil have similar toxicity. And so the dispersant isn't really doing anything except moving it into the water column. Dispersants do provide a greater bioavailability to aquatic life. So although we've moved it from the surface, so it's a lower risk to shoreline and surface-dwelling organisms like sea turtles and marine mammals, things like that, birds, it is going to be more toxic to aquatic life. Generally down to about 30 feet, which is 10 meters. The actual depth of dispersed oil into the water column really depends on wave energy and how well the application was. And then the last thing is impacts to subsurface resources are less obvious. It doesn't mean they don't exist. You just don't see giant amounts of floating dead fish instead of seeing dead sea turtles. So just a quick summary on some of the work we did in 2010 in support of the Deepwater Horizon. This was all, I blame this on our administrator at the time, Lisa Jackson. She decided that during the spill, because of the huge volumes of dispersants being applied and being requested, that we needed to do some toxicity assessment to see if there were other dispersants that might have lower toxicity. So this also, we wanted to verify the information on the NCP products schedule. Those are the list of approved dispersants that you as responders can pick from. We tested Louisiana crude oil, which was very similar to the Macondo oil. All of the data currently on the NCP are tested with fuel oil number 2, which was the old protocol. And then there was some concerns that, not for Crixit, but for some of the other alternative dispersants, they contained a small amount of chemical in some of those dispersants that could be degraded into a more toxic chemical called an endocrine disruptor. All right, so we did a lab testing program. We looked at efficacy. So this is all laboratory based. So it's not a wave tank. It's not field studies. It's just in bench scale work. But we looked at efficacy of the oil and the dispersant. We looked at in vitro. In vitro is like a test tube level. So you're not looking at whole organisms. You're just looking at cell lines. And then we looked at acute toxicity to 2 Gulf species. These are kind of standard test species. One of them is, let's see if I can get there it is. So this is a little, called a mysid. It's a little shrimp, and it's about 1/4 of an inch long, and then a little fish called a silverside. And these are native species to the Gulf of Mexico, and again, we use laboratory testing. So there's different ways to determine, well, how well do dispersants work, and comparing them. Well, what EPA has recommended and is in the National Contingency Plan is called a black baffled flask test. It's just simply a little glass jar that has it spins the oil and the dispersant mixture together with some water, and then we measure how much has actually made it into the water phase. I'm going to belabor you with a whole bunch of data, but we currently use this is subject to change, but we've used a kind of a bright line of, well, a dispersant should be 70% effective in order to be considered. So in this case, these are just a whole bunch of different dispersants, and this is effectiveness, and then here's kind of our magic line. Here's where 9500 came out, so it did pretty good. We also looked at this called cytotoxicity and endocrine testing. Again, these are cell lines, so not whole organisms. And these were only testing dispersant only. And so we looked at about 80 different types of test tube assays. We looked at cell death, and then something called estrogen and androgen activity. Estrogens will feminize a male, and androgen will masculinize a female. So these are just assays that would affect like hormone effects, potential, and then we tested a large range of different dispersant concentrations. And just to give you the quick answer, so this is kind of things, these are all done with little tiny test tubes, and it's all done through robots, and you're doing hundreds of different concentrations. But kind of the bottom line for this was similar results in all of the 8 dispersants, including Crixit, 9500. Didn't see any hormonal activity. And then we saw test tube cell death at about 10 parts per million, which you'll see is about the same as is for whole organisms. The next thing we did is looking at these 2 little test organisms. This is some example data from this little shrimp called a mysid. And so here, toxicity data, if you ever see it, is kind of counterintuitive. So in toxicity data, the bigger the number, the better it is. It's less toxic. And you go, well, how can that be? The way to view it is that if it takes more chemical to kill something, then it's less toxic because it took more. So I tried to make this more sense. And then EPA, we use a kind of a general scale to rank chemical toxicity. And you have like from non-toxic to slightly toxic to moderately toxic. This is 10 parts per million, which is kind of a bright guideline. And so anything above this line is not very toxic. And you can see dispersants alone, not very toxic. We also compared our data, the black data, to what was provided by manufacturers with fuel oil number 2. That's a middle distillate, like a diesel material, so not a crude. So just even though we had 2 different oils, the results were pretty reasonable. Crixit, right in about the middle. So then the next part of our toxicity assessment is we prepared dispersant and oil mixtures. And this is how you do this in the laboratory. So you start out with a big, like a carboy. It's supposed to simulate an oil slick. And so your oil's floating on top. Once you drop dispersant in there, it goes bam, bam, bam. After a period of time, you let it settle. You can see that some of the oil, even though when it's mixed, all of this oil was a tea-colored mixture. It looks like it's all been dispersed. But you can see, then we let it settle for 24 hours, and you can see some of the oil starts to actually coalesce and come back up. And then we would look at efficacy, we look at what's the dissolved in the water column, and then we test this material for toxicity. And these are just different dispersants. We did 8 different dispersants during the spill. You can see some of them are pretty good, turns them chocolate brown. All the oil stays in the water, and some don't. There's still always a little bit of remnant oil. This is the same kind of toxicity data. Again, less toxic. Remember, all the dispersants were above this 10 ppm line. All of the oil only, Louisiana crude oil only here, and then dispersant mixed, 8 different dispersants mixed with Louisiana crude. Really pretty similar. And just so you where Crixit was here, and this is if you just had the dispersant only. So some of the conclusions, maximum efficacy we see in the laboratory is about 80%. I know there's a lot of field assumptions where we assume it's 99%, 100%. It's not. It just appears to be, because a lot of that what initially is dispersed isn't broken up. The droplet size isn't small enough, and the oil recoalesces, but not when you're there. That's pretty well established. In vitro toxicity testing, not very toxic. Crixit overall, moderately toxic, and reasonable efficacy. So EPA is starting out on just this year now a new oil testing program. This work was all done in 2010 to support Deepwater Horizon. One of the things we're looking at, not sure if y'all worry about this yet, is dilbits, diluted bitumens. These are the things from the Canada tar sands that they're already being transported down to like Houston to the refineries. But if Keystone comes on board, things like that, there'll probably be a lot more diluted bitumens probably entering the environment at some point in time. We don't know much about the toxicity. We don't know about the dispersibility of it. Now it'd be most likely be a freshwater spill, so we're not worrying about dispersants with the dilbits, but we are trying to develop some baseline toxicity. The other thing we're doing, and in part because EPA got over 80,000 comments on the revised Subpart J rule, which determines how dispersants will be listed and monitored and tested. And so we are starting out probably in January to develop baseline data under the new proposed testing guidelines. So this would, we're also going to identify 2 new reference oils. The old EPA reference oil was Louisiana crude oil. We've depleted that, and so we're now identifying 2 types of oils that would be part of the dispersant listing procedure. We're going to evaluate some selected dispersants. We're not going to test everything that's that's currently listed, but we'll pick out some, and then we're going to expand beyond the standard guidelines. So basically what we're going to do is we've proposed how the new rule for listing will be, and we're going to test drive that for efficacy and toxicity to make sure that what we're proposing is reasonable. And we'll probably refine the proposed rule based on public comment that we've all gotten, as well as what we find in new testing. Okay, so I'll just wrap this up. These are kind of the implications for spill response. I just have these last 2 slides. So effectiveness. What does dispersant effectiveness depend on? Accuracy application, as you would suspect. Oil type and weathering. Heavy crudes, bunker Cs, fuel number 6, really heavy oils. They aren't very dispersible. And weathering, very highly weathered oils don't disperse very well, and it has to do with loss, because when you weather oil, you lose the lighter materials, which are the most dispersible. That's why they don't work quite as well. And it depends on how well they're mixed with oil. If it's dead calm, it's not appropriate. There isn't not sufficient wave energy to mix the oil and the dispersant. It'll look like you hit it, it'll turn brown on the surface, but it's not going to be put into the water and break into those really critical small droplets that y'all need for effectiveness. So, and then if there's a lot of wave energy, obviously natural dispersion will probably do the job. As I said, you're going to have reduced risk to shorelines and surface species, which is the reason you all disperse oil. But you're going to have increased risk to subsurface species. I think that's something that's not generally recognized. Standard toxicity testing, we are only evaluating with these little lab tests, these bench scale tests, short-term toxicity. Sublethal long-term toxicity, like was more the scenario for Deepwater Horizon. These tests don't really assess that. And then finally, this is my suggestions of questions you might ask yourself, and it's based on a lot of years of dispersant field and laboratory research, and that is, will mechanical response be sufficient? Obviously, that's your first choice. Is the spilled oil known to be dispersible? Are sufficient chemical response assets available, obviously? Are the environmental conditions conducive to dispersion? And and this is the critical trade-off, I think, is will the application reduce surface water and surface and shoreline impacts without significantly increasing aquatic life impacts? And that's all I have. If we don't get your questions answered at the end of today, you can send me an email. This is on the PDF, and I'll be happy to help you out.